So good morning, one and all. Today I, Anurag, is present here to present before you all our paper on detection of Alzheimer's disease using extreme band powers in EEG data. So let me give a brief intro of Alzheimer's disease. So it is basically a progressive neurological disorder that affects memory and thinking skills, and in the long run, it affects day-to-day tasks of an individual. So there are on an average 10 to 30 million cases worldwide each year. And currently, if we talk about the diagnostic measures, there are no such methods which can detect this disease in the early phase. So which leads to lack of treatment of this disease. And these are some of the relevant works. And the first one basically this work used the same data set as we did. And talking about the data set in short, so it is a publicly accessible data set, and we took it from Open Neuro. It comprises of scalp recordings, scalp EEG recordings of individuals. There are 36 Alzheimer disease patients and 29 healthy subjects, and 1020 electrodes system is used. And regarding the duration, on an average 13.5 minutes is taken. And you can see the electrode placement of the 1020 system of electrodes. And below is the electrodes in order, numbering from 1 to 19. So there are basically 19 electrodes. So briefly talking about the methodology, so we have the EEG data. So we are pre-processing it, and then feature extraction is taken place. Then we finally select the features which is of our relevance, and then the classification happens. So in pre-processing, what we are doing is that, so we are considering the first 550 seconds of this channel. So why 550? This is purely experimentation. Like we tried intervals even higher than this, but there was no better result. So there's no point of taking longer durations. So we took the first 550 seconds and broke that into intervals of 5 seconds each. So we have 110 such intervals for one channel. So the main features which we are considering here are the relative band powers of the 5 different frequency bands, namely delta, theta, alpha, beta, and gamma. And another additional thing is the Zort complexity feature. Basically, this Zort parameter helps to calculate the rate of change of frequency, which is much needed in this Alzheimer detection, because in these kinds of neurological disease there are small fluctuations which we need to consider in EEG signals. So in a channel, these feature values are calculated for each of the intervals. So in total, for one patient, we have 19 channels, 110 intervals, and 6 values of these 6 features. So we have these many parameters before. Now we will be looking to optimize these parameters, as this is too large for a model and model can hallucinate because of this. So we calculated the mean and standard deviation, and we are considering only those intervals whose value lie in greater than this range, mean plus 2 times of SD or mean minus 2 times of SD. So in short, we are just considering the extremities in this. And so this reduces to 19 into 2 into 6. From 110, we have just got 2 values. And also for these two ranges, we are calculating the mean of these two intervals. So this brings down the value to 19 into 2 into 6 per patient. So another thing is that why we are taking mean of only the extreme values, why not directly the mean of the 110 intervals? So there's a simple data example for this. Like basically taking considering the extreme values, it helps us to get the fluctuations present in data. And if we only consider the mean, we the fluctuations are like we cannot get the fluctuations present here. Like you can see both these data sets has the same mean. So one important observation was that there were no intervals lying in the upper range, that means greater than mean plus 2 times SD in case of the alpha band feature, and for all other bands there were no intervals lying in the lower range. So this further reduced our parameters. So this is basically we calculated correlation. So what we did was that we took one feature and one channel at a time and calculated the correlation. Correlation was the Pearson correlation with the uh, with the field that if the individual is having the disease or not, 0, 1, that field. So we put these channels in descending order of correlation. Say for this one feature delta band, this number 10 channel has the highest correlation, and this number 2 channel has the lowest correlation. This is done for all the features. So this was done to calculate the most relevant channels across all the features. So this is basically a heat map of the last one, last table which we see. So another observation here is that the beta and gamma bands have a very low correlation values for each channel. As you can see here about the beta and gamma bands, so the correlation is very less in case of this beta and gamma bands. So we can ignore these two features because this will not add any value to for our classification. So this another thing is that so 9, 10, 15, 16, these are the channels which are coming in every feature we have. So and 9, 10, 15, 16, and these also avoids by the domain knowledge that Alzheimer initially affects the temporal and parietal lobes. This channel lie there in the temporal and parietal lobes. And another thing which we did was calculating the correlation among channels. Say, for example, we have one feature. So channel 9 and channel 10, if you see, these are highly correlated. And similarly, channel 15 and channel 16 are highly correlated. Like this is like kind of maybe because these channels lie in close proximity to each other, so their readings are quite similar. So we did another thing is that out of this 9 and 10 we considered only one, and out of 15 and 16 we considered only one. So this finally brought down from these many parameters to 9 parameters, like 9 features per subject. Then for classification and validation, we used leave one subject out method, and different types of classifiers were used, like support vector machines, decision trees, logistic regression, random forest, and all. And this is the result. So first table gives the result of the paper, like which I said before, which use the same data set, and the table below gives our results. So we with random forest classification, we achieved 80% accuracy and 81.69 of F1 score. And concluding briefly, the left central, left temporal, right parietal, and the midline central, and this midline parietal. These are found to be the most important regions for this Alzheimer patients. Basically, the channels I talked about 9, 10, and 15, 16. And this also supports the fact that Alzheimer affects memory, like which is like left temporal lobe is responsible for that, and sensory integration, which is like parietal is responsible for that. And in future, like we are trying to explore integrate this method with other data sources like clinical assessments or cognitive assessments, neuroimaging, like to improve the accuracy. And these are some of the references used. Thank you and have a nice day.